Welcome back to the deep dive. If you are following the development cycle of artificial intelligence right now, and I mean, who isn't? Circa 2026, the only real constant seems to be acceleration.
It's an incredible pace.
Right. New models are dropping what feels like every few weeks, and each one is gaining this new level of complexity and capability that's just fundamentally reshaping everything. Commerce, creativity, knowledge work, you name it.
And that acceleration forces us to ask different questions.
Exactly. The central question for us, for humanity, isn't really if AI changes civilization anymore. It's about how quickly, and maybe more importantly, what sort of structural limits we're about to slam into.
And that's exactly where we are focusing today. In this, high velocity transformation, we tend to fixate on the visible things.
The hardware, the algorithms.
The hardware, the algorithms, the sheer scale of the training data. But we frequently overlook the most fundamental input to these massive systems.
And the language itself.
The medium of communication. Our technical deep dive today is going to explore a pretty radical idea, which is that our current suite of natural human languages has actually become a measurable technical bottleneck for the modern AI era.
Okay, let's unpack this, because when we talk about maximizing AI capability, we jump straight to designing the next transformer architecture or finding some huge algorithmic breakthrough.
Of course.
But we often skip over that foundational layer, just the words we use. Our sources today, and they include a range of linguistic analysis papers and computational complexity studies, they make a really compelling argument.
And the argument is?
That the speed, the efficiency, and ultimately the scalability of AI are now limited by the sheer technical inefficiency built right into human language.
That inefficiency, it's not an abstract concept. It's rooted in the, let's call it the computational physics of large language models, or LLMs.
Right.
Every thought, every prompt, every single piece of knowledge, whether it's text or code, it has to be converted into these discrete units, tokens. And that tokenization process is, it's the lingua franca of the machine. The core technical friction here is actually pretty simple.
The more tokens, the more work.
Exactly. The more tokens required to express a single unit of information, the higher the computational demand. So if English takes, say, 8 tokens to express an idea that some optimally designed language could express in just 2, you've just created a 6-token inflation factor.
And that inefficiency isn't just a linear drag on the system. It must accumulate exponentially.
It does. It has to.
I mean, if you're talking about training runs that involve trillions of tokens across thousands of GPUs, pushing those, 6 extra tokens through the pipeline for every single conceptual unit, that's going to translate directly into massive capital expenditure.
Right. And increase energy consumption.
And slower training, slower inference times. It touches everything.
It touches everything. The inefficiency is a hard constraint. It's tied to cost, to energy usage, and to physical deployment limits, especially when you start thinking about real-time or, edge AI applications.
So that really defines our mission for today. We have to synthesize the engineering requirements for a language that's designed from the ground up to just eliminate this friction.
That's the goal.
So, okay, let's define the required technical optimizations. What are the, say, 3 non-negotiables for this post-natural language?
They really fall into 3 main pillars of optimization. First, you need maximal information density, and we can measure that in bits of meaning per token.
Okay, density. What's number 2?
Second, we need grammatically enforced expressions of certainty and doubt. And this can't be vague. It needs to be calibrated at these fine-grained probabilistic levels. We might even call it something like quantum-like granularity.
Wow, okay. And the third?
And third, we need rich, structured emotional nuance embedded directly into the grammatical structure itself.
So the ultimate goal here isn't just to make a slightly more efficient version of English.
Not at all.
It's about designing a high-bandwidth, low-latency communication environment. It's like building the necessary infrastructure for a seamless human-AI symbiosis.
It is. It's about unlocking higher cognitive potential and communication efficiency by, in effect, upgrading the linguistic operating system itself.
It's a recognition that for AI to really reach its full potential, we just can't rely on languages that evolved in the Stone Age anymore.
We need one designed in the age of the transformer.
That brings us directly into analyzing the technical inefficiencies baked into the languages we all use every day, starting with what feels like the core conflict, the evolution versus optimization problems.
Yeah.
These languages were never intended for digital processing.
And that distinction is absolutely vital. I mean, look at the origin of natural languages. They evolved for oral transmission.
Spoken word.
Spoken word in small, often geographically isolated communities. And in that kind of environment, the single most important design criterion wasn't efficiency. It was robustness.
You needed to be understood.
You needed to be understood, which required high levels of redundancy.
Right. If I'm shouting at you across a noisy field, or if a word gets muffled, that redundancy, repeating the subject, using predictable grammar, adding descriptive words, that was a feature, not a bug. It ensured comprehension.
It prioritized robust delivery over compression.
But now, today, that same robustness creates measurable technical friction inside a transformer architecture.
Yes. When an LLM processes information, all that grammatical and lexical redundancy, it translates directly into those longer, more complex token sequences we just talked about.
Can you elaborate on the computational drag this creates? I mean, why is it more than just a slight increase in cost?
Well, think about the attention mechanism in a transformer. It's the core of the whole thing. It has to calculate the relationship between every token in a sequence and every other token.
Okay.
So if you fragment a single unitary concept into, say, 10 tokens, the model now has to process and retain these really complex long-range dependencies across that entire sequence just to reconstruct the original idea.
And that's computationally expensive?
It increases the complexity of the attention matrix and the computational load. Well, it's calculated based on the square of the sequence length. Longer sequences mean exponentially higher processing costs. And, critically, they chew up the limited context window.
So the analogy of sending a compressed JPEG file versus an uncompressed, like a raw image file, becomes really critical here.
That's a great analogy.
I mean, both convey the image, but that raw file requires vastly more processing power, more time, and crucially, more memory, which is the equivalent of the context window, just to handle that uncompressed data.
Precisely. If our goal is to get models with context windows that can handle an entire novel, or maybe hundreds of pages of complex scientific documentation, every single unnecessary token is a wasted byte of memory and a wasted cycle of computation. The written forms of languages simply vary too dramatically in their intrinsic digital density.
And while this sort of evolution-first problem plagues most languages, we do have to acknowledge that not all natural languages are created equal in their inefficiency.
No, they're not.
Our sources highlight a pretty significant, if accidental, technical advantage in logographic systems.
This is a crucial data point in the argument. Languages like Mandarin Chinese, they offer a tangible advantage, and it's all through logographic density.
Because a single character can be a whole word or concept.
Exactly. Because a single character often represents an entire concept or morpheme, a unit of meaning, rather than just a sound. They require significantly fewer tokens to convey the same meaning compared to an alphabetic language like English.
And what we're seeing in recent AI research is that this density advantage isn't just theoretical. It translates into real, measurable performance differences.
Oh, absolutely. Especially in complex reasoning tasks.
How so?
Well, when a model can encapsulate a complex, high-level idea like sustainable infrastructure development in, say, 5 tokens instead of 15, it retains the conceptual integrity of that idea much more easily within its context window.
It's less likely to get lost in the noise.
Exactly.
Yeah.
It reduces the chance of semantic drift over long sequences.
Mm-hmm.
And we've seen studies that have shown models demonstrate superior reasoning and better factual recall in complex, multi-step tasks when they're processing data in these high-density languages.
So it's effectively giving the LLM a bigger working memory just by providing it with a more efficient instruction set.
That's it. It's like operating a CPU with a more efficient machine code.
It's that fundamental.
Correct.
Yeah.
However, and this is the really vital caveat, even a language like Mandarin is an optimized accident. It's still constrained by its historical roots, by calligraphic demands, the need to be pronounceable by humans.
Wasn't designed for silicon.
It was optimized for efficient written representation by hand and for human memory, not for a transformer's token space. So we're taking that density lesson from Mandarin and we're asking, what if we designed a language that was deliberately optimized for digital entropy compression from day one?
Okay, so beyond density, the other massive technical headache you mentioned is the inherent ambiguity built into natural languages.
Yeah.
Particularly when it comes to degrees of certainty and emotional state. Our sources call this cognitive overhead.
And cognitive overhead is the perfect term for it. It's the measurable technical cost of parsing ambiguity. Just take certainty.
Right.
When a speaker uses English adverbs like probably, maybe, or almost certainly, these terms, They lack any precise standardized calibration. Linguistically, they're just vague lexical tool.
Or fuzzy.
Extremely fuzzy. If I say the simulation is likely to converge, that could mean anything from 51% certainty all the way up to 95%. The listener, whether it's a human or an AI, has to infer the true probabilistic commitment based on context, domain knowledge, the speaker's past behavior.
And that inference, that guesswork, must be computationally expensive for an LLM to perform reliably. I'd imagine it leads to high error rates and the need for constant clarification.
You're exactly right. The LLM has to run an expensive predictive model over the entire context just to assign a confidence interval to those vague adverbs. And then you have the problem of emotional subtlety.
Oh.
To accurately convey complex, affective states, a blend of cautious optimism and professional regret, for instance, you often need paragraphs of context, tone of voice, or descriptive phrases.
You're forcing the AI to infer sentiment from completely unstructured data.
And these limitations, when you scale them up across global remote technical collaborations or in critical human-AI interactions, they introduce massive potential for misalignment and misunderstanding. The language is actively forcing both us and the AI to constantly guess.
Guess at the speaker's true probabilistic commitment and their underlying effective stance.
Yes, and that severely degrades the quality and the efficiency of the entire communication channel.
So if our natural languages are technically holding us back, we need some blueprints. This brings us to the prior art, looking at both naturally evolved linguistic features that offer some solutions and, well, some radically constructed languages that prove extreme engineering is at least possible.
And we begin by solidifying that first pillar, density. The big lesson from nature is that logographic systems pack semantics into compact units, and that grants significant token savings. We need to see this not as just a linguistic curiosity, but as a demonstrable technical result with a financial bottom line.
Can we put a more concrete figure on this token saving? How much are we really talking about?
In many common tokenizers, simple English phrases like computer science or artificial intelligence will often break into 2 or 3 tokens, sometimes even more. The tokenizers prioritize common word parts over the integrity of the concept.
Okay.
In high-density languages, those same terms are often represented by 2 or 3 logographic characters, which usually tokenize down to 1 or, at most, 2 tokens.
So we're talking about reducing the input length by a factor of 2x or even 3x for these kinds of high-information phrases?
At least. And this compaction is mathematically proven to deliver faster LLM training and inference, which, when you scale it up, translates directly to a cost reduction in the millions of dollars.
That's the efficiency lesson. Now, the second crucial technical pillar is precision, specifically around certainty. And here, we find this fascinating concept of evidentiality built right into hundreds of natural languages.
Evidentiality is a breakthrough concept for this discussion because it shifts certainty from being optional context to being a mandatory structural requirement of the grammar.
A mandatory requirement?
Yes. Over 200 languages worldwide, including Tucanoan languages in South America and various languages in the Himalayas, they grammaticalize evidentiality. It's not optional vocabulary, it's a mandatory morphological marker, often attached right to the verb conjugation or the core predicate of the sentence.
So if I were speaking one of these languages and I wanted to assert the fusion reactor reached critical mass, I couldn't just state the fact.
No, you couldn't.
The grammar would force me to justify how I know it.
Absolutely. You'd be forced by the language to include a morpheme that indicates the source of your evidence. Did you witness the event directly with your own eyes? That's visual evidence.
Or did you hear the alarm bells and sirens?
Auditory evidence. Or maybe you read it in a report written by a third party, which would be reported or hearsay evidence. Or did you infer it from the data and the models you were running? That's inference. Each one requires a different grammatical marker.
This is a massive technical insight. It instantly packages the source credibility, the degree of certainty, directly into the data payload.
It moves from being a vague, contextual inference to a structured, mandatory data point. It gives us a perfect natural foundation for engineering those granular, probabilistic markers we need.
It standardizes the source attribution.
It does. And for an LLM, this mandatory marker acts as a built-in confidence score for the input data. It immediately enriches the quality of its reasoning and prevents it from treating, say, inferred data with the same certainty as directly observed data.
So if natural languages offer these powerful hints, constructed languages provide the absolute technical ambition. This leads us to what many consider the gold standard of engineered precision, Ithkuil. And here's where it gets really interesting, because Ithkuil basically shows us the absolute limits of linguistic engineering.
Ithkuil, which was designed by John Quijada, is a constructive language, and it was specifically engineered for extreme density, logical precision, and the explicit removal of cultural ambiguity.
It's an intellectual exercise, really.
Fundamentally, yes. It's an exercise to see just how much meaning can be packed into the smallest possible linguistic unit.
And the technical achievement is just staggering. The core thesis behind it is that a single complex word in Ithkuil can encapsulate a highly nuanced proposition that might require an entire clause-laden paragraph in English or Spanish.
Its grammar is just relentlessly anti-redundant. It achieves this density through a highly complex, agglutinative morphology.
Okay, what does that mean in simple terms?
It means it combines many morphemes, each one carrying a specific structured piece of information into one single continuous word form. This often leads to very long but incredibly informative single words.
So for our blueprint, for the language we're trying to design here, which specific morphological categories from Ithkuil provide the technical solutions to the inefficiency problems we've identified?
We have to highlight the categories that perform the semantic compression. Firstly, there's the category of perspective. And this isn't merely point of view. It specifies the relationship between the speaker, the subject, and the listener instantly.
For example.
Are you describing the whole thing, which is holistic, or just one part of it, which is partitive? This kind of distinction eliminates a huge amount of structural ambiguity right off the bat.
And then there's its system of validity, which tackles our certainty problem head-on.
Precisely. Ithkuil's validity system moves far beyond the natural evidentiality we just discussed. It forces the speaker to select one of 9 precise commitment levels to the truth of their statement.
9 levels.
9, ranging from observed fact all the way to hypothetical counterfactual. It's a very granular scale. This category forces explicit epistemic accounting.
This feels essential for our new language. It shows us how to collapse all those vague English adverbs, likely, maybe, possibly, into a single mandatory grammatical choice. It forces precision.
We also have to look at mood and the cognitive attitudes. The mood specifies the illocutionary force, that's the purpose of the Speech Act, with intense granularity.
And the cognitive attitudes.
The cognitive attitudes are built directly into the word's structure. They allow the speaker to express their emotional or intellectual relationship to the proposition itself. Are you stating this with excitement, with resignation, with skepticism?
So Ithkuil eliminates the need for tone of voice or descriptive context by hard-coding the speaker's psychological state directly into the grammar.
It standardizes effect. These features altogether eliminate ambiguity and express profound nuance with incredible conciseness. Now, Ithkuil is notoriously difficult for humans to learn. That complexity is its main barrier to adoption.
But its value for us is demonstrative.
Exactly. It proves the technical possibility of creating a grammatically rigorous system that maximizes density and minimizes ambiguity through radical design.
And the sources mention historical density efforts too, right? Something about classical Chinese.
Yes. Classical Chinese, while it wasn't designed for digital transformers, achieved extreme brevity through what's called a zero-marking strategy.
Meaning?
The lack of explicit tense, number, or subject markers in many contexts, it relied very heavily on context and implied meaning, achieving density through omission. Now, the future language we're designing must be explicit, unlike zero marking, but the core lesson, the pursuit of brevity, remains.
So the blueprint is becoming clear.
It is. Combine the density of logographic systems, the mandatory rigor of evidentiality, and the sophisticated morphological engineering of a language like Ithkuil.
This brings us to the core of our technical deep dive. We're moving from analysis and prior art to active design. We are now in our neural signal check, outlining the technical roadmap for the proposed language and why these developments matter at a fundamental engineering level.
Right. This is where we define the functionality that will truly unlock that next level of human-AI collaboration. We have to move beyond simply adopting existing features and actually design new grammatical categories to handle modern demands.
Specifically, the probabilistic nature of 21st century information.
That's a big one.
So let's start with extending certainty into what our sources are calling a Bayesian grammar. The goal here is to move beyond natural language's sort of binary or ternary evidentiality to really fine-grained scales.
The foundational constraint we're solving for is the total inadequacy of our language for scientific and risk communication. Modern life, From financial modeling to climate science, it relies on probabilistic thinking. It relies on Bayesian updates.
And our language doesn't reflect that.
Not at all.
Yeah.
We need to communicate not just how we know something, but how certain we are, using standardized, quantifiable metrics.
So we need to design a system that allows a speaker to communicate something like, based on these 4 sensor readings, I am 92% certain that the anomaly is transient. And have that 92% be part of the grammar, not just a number in the sentence.
Exactly. The design goal is to create fine-grained probabilistic scales that are mandatory in high-precision statements. And the technical mechanism for this would involve dedicated grammatical affixes or particles.
So these aren't just optional adverbs anymore.
No. They are inflections that must be selected from a standardized scale. For example, deciles of confidence, or defined ranges like 90-100% certainty, 50-90% plausibility, things like that.
Okay, can we detail how this would actually be encoded and then parsed by an LLM? How does it work under the hood?
Crucially, this system requires a defined morphological slot in the grammar that is dedicated solely to probability. Imagine a dedicated slot in the verb structure. The speaker must select a morpheme from a predefined set of, let's say, 10 probabilistic markers. When the LLM processes this sentence, it doesn't need to run a sentiment model to try and guess what likely means. The input token stream itself carries an explicit metadata tag.
Like verb root plus probabilistic affix 8.
Precisely, where FX8 is standardized across the entire language to mean 80-90% confidence. This provides clean, structured data for immediate reasoning. No guesswork required.
That structural requirement makes reasoning completely transparent. It forces the speaker into a kind of epistemic accountability. But what about those areas where certainty is actively fluctuating, like during real-time data integration?
That's a fantastic question, and that's where we can integrate linguistic markers that are analogous to what physicists describe as quantum levels.
Okay, you've got my attention.
We could design a grammatical state for superposition-like ambiguity. This would be a specialized affix indicating that a concept or a variable is currently held in a defined range of potential truths, pending further data integration or observation.
So the LLM would see this and know what to do?
Yes, the LM would recognize this grammatical state as unresolved variable, and it would prioritize incoming information that relates to it until a final resolving marker is applied, which would shift the concept to a definitive probabilistic value.
That is truly revolutionary. It forces the speaker, whether they're human or AI, to explicitly acknowledge their uncertainty. It provides the listener, or any downstream process, with an immediate, structured risk profile of the information being conveyed.
And the technical implication of this is paramount for the stability of AI systems.
Yeah.
This explicit grammar acts as a powerful preventative measure against the overconfidence biases that are currently plaguing LLMs.
The tendency to hallucinate.
The propensity to hallucinate information and present it with this unwarranted absolute certainty. If an LLM is forced by the structure of the language to state a probability of 0.770% instead of 1.0100% because its training data only supports 70% confidence, then the language itself imposes an epistemic guardrail.
So we've standardized uncertainty. That's huge. Now let's move to the other major design specification, grammaticalizing emotional nuance, or structured affective morphology. Why is structuring emotions so technically important for AI?
Because affective data emotions, feelings, intent are absolutely critical inputs for decision-making and for alignment. Yet they are the messiest, most unstructured data that LLMs currently have to handle.
It's all subtext.
It's all subtext and context. If we rely on the AI to infer sentiment, we open the door to massive misinterpretation, particularly across cultural and linguistic boundaries.
The AI needs to know if the speaker is communicating hesitancy or frustration or just curiosity, but it needs that signal packaged in a reliable way.
Exactly. So the design solution is to embed these affective categories directly into the morphology of the language, much like Ithkuil did, but optimized for digital transmission.
So instead of saying, I deeply regret the delay,
the verb for delay, or the noun for event, would carry a mandatory affix that indicates the speaker's precise emotional stance toward that proposition.
Which specific dimensions would we have to grammaticalize to provide these structured signals? What are we measuring?
We'd need 3 primary structured dimensions to define the affective space clearly. First is intensity, so the magnitude, mild, moderate, profound.
Okay.
Second is valence, the quality. Is it a positive, negative, or neutral charge? And third is intentionality.
What's that?
Is the emotion directed at a specific person or agent? Or was it caused by an external, non-agentive force, like a storm or a system failure.
That sounds incredibly structured. It's almost like you're defining emotion using a three-dimensional coordinate system that's attached to the proposition itself.
That is exactly the goal. It removes the ambiguity of tone of voice, of punctuation, of word choice. These structured affective categories would be encoded via designated morphological slots, maybe through a sophisticated system of fusion affixes that combine valence and intensity into a single compact unit.
This ensures the emotion isn't just descriptive flavor text, it's inseparable from the content.
That's right.
So this technical integration provides the AI with structured signals rather than forcing it to rely on ambiguous inferred sentiment. What's the technical implication for communication stability?
It leads to much greater stability in digital and cross-cultural communication, where all those vital contextual cues like body language are absent. This structured affective morphology enriches the AI's emotional intelligence.
And to be clear, not by making it feel, but by giving it data.
Precisely. It's not about feeling. It's about providing it with a stable, predictable basis for understanding human intent and preference. So when an LLM receives a prompt in this new language, it gets not just the propositional content, but the speaker's precise probabilistic commitment and their structured emotional engagement. That is maximum bandwidth communication.
It effectively standardizes empathy into the channel itself. The difference in input quality for the model must be enormous.
It's the difference between feeding the AI a stream of ambiguous text and feeding it a stream of highly organized, metadata-rich data packets. It improves the quality of the interaction and the reliability of any AI decision-making based on that human input.
This level of optimization, it promises massive returns, not just in raw machine performance, but potentially in human cognitive capability too. We're moving into our next section, the cognitive and practical benefits of optimization.
Right.
And we have to start with the human side and the famous, or maybe infamous, Sapir-Whorf hypothesis.
The Sapir-Whorf hypothesis, yeah. In its simplest form, it posits that the structure of a language influences or even shapes the native speaker's cognition and their worldview.
So in the context of our engineered language, the sources are suggesting that imposing this kind of rigorous, unambiguous structure will actually compel the speaker to adopt a similarly rigorous mode of thought.
That is the hypothesis.
If the language forces us to communicate with mandatory probabilistic and effective markers, it almost forces us to think in that structured way. It requires us to constantly assess our own certainty and emotional state before we even speak.
Exactly.
What are the cognitive gains we're hypothesizing from this kind of linguistic structure?
We're hypothesizing two major gains. First, the mandatory probabilistic and evidential markers would, over time, cultivate better epistemic humility in human thought.
Better thinking habits.
Better mental habits. If you are grammatically obligated to state your confidence level, say 65%, or your source of evidence, like inference, not direct observation, it constantly reinforces a scientific, cautious, and data-driven approach to knowledge claims. It inherently reduces fallacies that are rooted in overconfidence or generalizing from anecdotal evidence.
So the language itself becomes a kind of permanent cognitive training regime for critical thinking and data-based communication.
Precisely. And the second potential gain comes from the dense morphology. If a single, tightly packed construction can convey a complex, multi-layered idea, a multivariate analysis with specific affective and probabilistic commitments, that currently requires a long, winding, context-dependent English sentence.
Then you can think faster.
This dense morphology could actually accelerate idea formation and conceptual manipulation in the mind of the speaker. It reduces the sheer linguistic scaffolding you need to hold complex concepts together in your working memory.
That's a profound thought. Engineering a language to make us better, faster, clearer thinkers. You could jump straight to the complex idea without spending all that cognitive energy on just grammatical assembly.
That's the hope.
But let's turn to the hard, practical performance metrics. So what does this all mean for the bottom line and for the deployment of AI worldwide?
This is the financial argument, and it's a technical slam dunk. The core practical benefit is that for AI, a native efficient language would significantly slash token costs. And this isn't theoretical.
Right, we see it already.
It's the measurable financial impact we already see with high-density natural languages, just amplified by deliberate optimization. Since every unit of information is compressed, the necessary memory footprint and computational load per request just drops dramatically.
So if the language is 2x or 3x denser than English, we are literally talking about cutting inference costs by half or more. What are the results of slashing those costs? What new capabilities does that unlock?
It enables crucial breakthroughs that are currently bottlenecked by cost and memory. First, it allows for longer contexts,
Better memory.
a much better, more consistent memory and coherence over extended interactions. It effectively solves the short-term memory problem that plagues current models when they have to process long sequences. A cheaper token allows the context window to be exponentially larger for the same price.
And secondly, the cost reduction, that leads directly to massive scalability.
Absolutely. The reduction in inference cost globally allows for cheaper deployment of AI agents across vast infrastructure. Think real-time translation, specialized knowledge assistance in low-resource environments, or mass-market consumer AI tools.
It democratizes access.
It democratizes access to sophisticated AI by fixing the structural cost of the input itself. We would be universally amplifying the density advantages we already see in models trained on languages like Chinese, and that makes the technology faster, more intelligent, and far more accessible worldwide.
Finally, we should probably consider the immediate practical application of a language like this. Not as a total replacement for daily conversation, but maybe as an auxiliary precision tool for specialized domains.
That's its most immediate and powerful utility. Such an optimized language could serve as a neutral auxiliary for high-precision, high-stakes domains.
The applications are huge.
Imagine it. In science, where precise confidence intervals are mandatory for publication. In diplomacy, where nuanced emotional and propositional commitment has to be structured to mitigate misinterpretation. Or even as specialized ultra-dense programming interfaces for software documentation or complex automated systems.
It becomes the high-definition, low-friction channel you switch to only when accuracy, speed, and transparency are completely non-negotiable.
Exactly. It will be adopted by technical communities globally who are already frustrated by the inherent ambiguity of English. Now, the big caveat we must stress, drawing from the failures of languages like Ithkuil for mass adoption,
It has to be learnable.
it must remain learnable through a modular structure. The rules have to be systematic, predictable, and totally devoid of the linguistic irregularities that plague natural tongues. This is what ensures it gets adopted as a usable, practical tool and not just a theoretical construct.
We've conducted a really comprehensive technical deep dive into the blueprint for synthesizing a post-natural language for the AI era. To just synthesize and recap the argument, natural language, while it's a miracle of evolution, offers imperfect, accidental optimizations.
A fact that's highlighted by the existing linguistic edge we see in models trained heavily on Chinese data.
And to transcend these constraints, we need this deliberate blueprint for the future language. It has to be engineered to be hyper-dense, probabilistically precise in its grammar through a Bayesian structure.
And emotionally articulate through structured morphology. We're drawing inspiration from the radical precision of Ithkuil, the mandatory rigor of natural evidential systems, and the raw efficiency of logographic density.
This feels like more than just linguistic engineering. It's like we're laying the foundational cognitive and computational infrastructure for the next stage of human and artificial intelligence evolution.
Indeed. And we have to frame this new language not as a replacement for our natural tongues, which, they carry our culture, our history, our identity, but as an augment to them. A precision instrument for clarity, for high-speed knowledge transfer, and for complex, rigorous thought. It is the necessary bridge to higher bandwidth human-AI communication.
And the ultimate implication of successfully engineering this tool, what's the end game?
The endgame is that this optimized language will equip humanity and our AI partners for clearer thought, deeper connection, and an unprecedented intellectual velocity in this information age. By maximizing the efficiency of the communication channel, we ensure that our future thoughts are communicated with minimal friction, maximal precision, and explicit epistemic accountability.
That raises a final provocative thought for you, the listener, to mull over. If the structure of our language really does dictate the structure of our thoughts, and our current languages impose these costly computational and cognitive bottlenecks, then the time to begin designing this new language, this highly efficient operating system for the networked mind, is now. We are suggesting that the very fabric of our future communication is not a passive matter of evolution, but a critical, urgent design choice we can and must actively make.
So we'd encourage you to start examining your own language. Identify those areas of ambiguity and unnecessary redundancy, particularly in your technical documentation or your collaborative workflows. What specific inefficiencies are you encountering in your current AI workflows that could be solved by a mandatory grammatical redesign, one that forces clarity where right now there is only inference?
Thank you for joining us for this deep dive into the technical specifications of language design for the AI era. To stay updated on the latest in AI and ML, visit our webpage, neuralintel.org, and check us out on YouTube. Until next time.